Hi, welcome back to Elasticity. Today we are going to look at Hooke's law, which is what we talked about last class, and we will see what kind of constants, material moduli can you get out of particular tests. So if you remember last class, and I'm going to try and see if I can show you what we had last class. So we had this matrix, right? And we are now going to see what kind of measurements can I get out of looking at these numbers. Okay, so let us see what will happen. A uniaxial stress sigma 11 of magnitude 20 megapascal was applied to a dog bone specimen. That means specimen that looks like this. And the following strains were measured. Epsilon 11 equals, let's put some number, 0.001. Epsilon 22 equal to 0.0001. Epsilon 33 equal to 0.0002. Epsilon 12, so negative. Epsilon 12 was 0.0001, sorry, yeah, and epsilon 13 equal to 0, epsilon 23 equal to 0. This is what we got. Notice that the strains are dimensionless, whereas the stress dimensions are megapascal. So what constants can be determined? In the compliance matrix. So according to our compliance matrix, epsilon will be equal to S times sigma, and this is sigma 11000000. So there's 6. Can you see that? So if you do this multiplication, the first column will be found because that's the only thing that matters. So let us see. According to our matrix, from here I will get epsilon 11 is S1111 sigma 11. Epsilon 22 is S2211 sigma 11. Epsilon 33 equal to S3311 sigma 11. Then epsilon 12 is S1211 sigma 11. Epsilon 13 is S1311 sigma 11. Epsilon 23 equal to S2311 sigma 11. So it's pretty easy to find because S1111 equals epsilon 11 over sigma 11, which turns out to be 0.001 divided by 20 megapascals. This is 1 over E11. So this, which implies E11 is 20 megapascals. Sorry about that. Let's do that. Divided by 1 times 10 to the minus 3, which turns out to be 20 GPa. and S1111 equal to 1 over 20 GPA inverse. That was easy. Next one, S2211 is epsilon 22 over sigma 11. That turns out to be 0.0001 negative divided by 20 megapascals, which is equal to 1 over 200 GPA inverse negative, right? So, but we are interested maybe in Poisson's ratio. Is actually negative of epsilon 22 over epsilon 11, which is equal to negative of 0.001, that's plus, divided by 0.001, which is 1/10, which is 0.1. It's the Poisson's ratio. This is called nu 1 2, right? You can do, so what do you think nu 1 3 will be? What about S1311? So S1311 is easy. This is 3311. S3311 is easy. It is minus epsilon 33 over plus epsilon 33 over sigma 11, which turns out to be, how much is epsilon 33? Epsilon 33 is minus 0.002 minus 0.0002 divided by 20 megapascals, which will turn out to be minus 1 over 100 gigapascal inverse. What about nu 13? That will turn out to be epsilon 33 divided by epsilon 11 negative, which if you calculate will turn out to be 0.2. Notice that the Poisson's ratio in different directions are different, right? Of course, if you know the Poisson's ratio, you can find this, because you can see by a very quick calculation S33 nu 13 nu, I should have been more careful, it is nu 31, apologies, so this should be so this should be nu 31, which is equal to S3311 times E11 negative, and that will also turn out to be 0.2. You can try that, you will see. Okay, so you can either calculate it from S or from nu, and this information, one tension test will give you one whole column of the matrix. If you do 3 tension tests, you will get the first 3 columns. If you do 3 shear tests, you will get the last 3 columns. So you'll get the 6 columns. So you have to do, but when you do a tension test, it's not enough to just measure E11. You have to measure everything, E11, E22, E13, etc. So each tension test will give you one whole column of this matrix. So this is called, by the way, Hooke's law. And I kind of was very casual about the temperature dependence. For example, I did not talk about the volume expansion. So what happens is, it's not really volume expansion. So imagine I had something. So there is nothing which says that if you heat something, it will just expand uniformly. So if I take a sphere of something, our original idea, if you looked at your strength of materials class, is that a sphere will become a bigger sphere if I heat it. But imagine I had a sphere which had wires on it this way. Most likely when I heat it, it will become like this. it won't expand that much in the radial in this direction as it will in this direction if this is very stiff and low expansion. So that's why my volume expansion coefficients or the thermal expansion coefficient has 6 numbers for axial stretches as well as for shear. For all you know, if I heat something, it will shear. It would be very interesting materials if you can make things do that, because then you can have interesting deformations by playing around with one kind of constant, one kind of stress and getting another kind of displacement. Okay, so this is how we compute the Hooke's law, the components in the Hooke's law. Thank you.